Hey everyone, thank you for coming to today's Tech Talk. As always, we will have a Q&A session at the end of our talk. So throughout the session, please give us questions and we will take time at the end to ask those. So today I am very excited to introduce Dr. Manil Maskey. He's coming to us from NASA, and so currently Dr. Maskey is working on developing artificial intelligence and machine learning strategic roadmaps for the Earth Science Data Systems program. In addition, he is working with the Marshall Space Flight Center. He is leading advanced concepts team for the interagency implementation and advanced concepts, or the IMPACT project, where he develops data-driven solutions to challenging Earth's problems. Dr. Maskey's career spans over 20 years in academia, industry, and the government. During that time, he's focused on research and application projects in the area of data systems, machine learning, computer vision, and visualization. So thanks, Dr. Maskey, for joining us. Go ahead.
Hello, everyone. Thank you for having me. I would have preferred to be there in person giving this talk, but given the current circumstances, I'm happy to do this virtually. As Aaron mentioned, my name is Manil Maskey, and I work for NASA, where I work on a wide range of projects, including developing modern data systems, applying novel techniques on Earth observation data to solve real-world problems, and developing strategic roadmaps for technologies to be infused into the program. My PhD is in computer science. However, I've worked across various domains over the past 20 years, starting in the industry where I built products. Then I moved into academia where I did fundamental research. And now I'm in the government side where I'm involved in tackling real-world applications using data-driven approaches. I realize that the types of data that we deal with NASA science are different from what you all are probably used to, but I hope the approaches are informative and maybe even applicable in some cases. So let's get it started. So NASA has a bold vision of reaching for new heights and revealing the unknown for the benefit of humankind. So that's pretty bold, right? With that vision, NASA's mission is to drive advances in science, technologies, aeronautics, and space exploration. To do so, NASA helps answer humanity's fundamental questions. How did the universe begin and evolve? And why? What will be its destiny? How did life originate, and are we alone? How are Earth's climate and environmental changing? NASA also puts a lot of emphasis on innovation. Every mission that NASA conducts advances the state-of-the-art in that particular area of technology. Most of the spin-offs improve lives, keeps us safe, and also fuel the commercial industry. And of course, NASA helps inspire a new generation of scientists, engineers, and explorers by providing a gateway through various types of STEM-based careers. One of the NASA's strategic goals is to observe our planet comprehensively to address science questions, as well as societal applications. Studying home planet, that is the Earth, is central to our lives. Hence, Earth science plays a vital role in NASA's missions. In order to study the Earth as a whole system and understand how it is changing, NASA develops and supports a large number of Earth-observing missions. These missions provide Earth science researchers the necessary data and addresses the key questions about how our planet is changing. In that sense, no planet is better studied than the one we actually live on. Here you see NASA's fleet of Earth science missions in space, supported by international types of observations. They measure everything from the air we breathe to the rain and snow that provides water to the agriculture and communities, to natural disasters like hurricane and droughts and floods. So this visualization shows what's coming up until through 2023, and you can see the scale of the missions that we have coming up. This animation shows the orbits of NASA's fleet of Earth-observing spacecraft that are considered operational at the end of last year. These are continuously collecting data to study the planet. Additionally, we have satellites and instruments on International Space Station that circle the whole globe, seeing both where people live and those people, remote places where we can't see from the Earth, right? So it's helping us study these remote parts of the world that we cannot visit. The Earth Science Data Systems program that I work for actively manages NASA's Earth science data as a national asset. It develops capabilities optimized to support science investigations. It also processes and reprocesses, in some cases, instrument data to create high-quality, long-term records of Earth science, Earth information. So our primary goal of the program is to maximize the use of, maximize the scientific return from these NASA's missions. In some cases, these are very expensive missions. So the program manages the Earth science data through the entire data lifecycle, as you see here. Within the data lifecycle, once the mission generates the data goes through processing to create a high-quality, long-term Earth science records. These data are complemented with detailed documentation so that people can easily use them. Additionally, the lifecycle includes unique data system capabilities optimized to support rigorous science investigation and research by providing these advanced search, access, and distribution capabilities. So why is it important to provide the data stewardship for the Earth science data that we collect? To answer that question, we need to look at this study conducted by NASA's ad hoc Big Data Task Force, which stated that half of all science results come from archive data, right? When we archive this data, people are doing these researches that are doing a lot of this major findings about Earth and its processes. So over the past 25 years, millions of users around the world have benefited from these policies that we have set forth, which includes open data policy, open source software, and open services that we provide. Having this continuous flow of data available for researchers have made development of new applications and even in some cases commercial innovations. By looking at the numbers, you can see that we had about 34,000 unique data products. This is as of end of FY fiscal year 2019. About 462 million files, 3.5 million distinct users, and about 1.9 billion products distributed. The archive at the end of FY 29 stood around 34 petabyte. And all of that, we're doing all of that with a customer satisfaction index of 78 out of 100. So looking at the future, this animation shows how the archive will grow in coming years, mainly driven by high data volume missions. By 2022, the ingest rate of the data into the archive is projected to grow from current rate of 4 petabytes per year to as much as 48 petabytes per year. As this ingest rate increases, the total volume of the data stored in the archive is also expected to grow from its current size to up to 250 petabyte by 2025. So this anticipated growth in both the data ingest rate and as well as the overall archive volume creates a challenge for archiving, distribution, and analysis of the data. This animation shows data collected by various instruments aboard a NASA platform called Terra, which recently completed about 20 years in orbit. So imagine the amount of data that is being collected, continuously collected for 20 years from these 6 instruments. And also extracting the geophysical parameters, like you see here, and applying that information to make major decisions, right? It's pretty neat. However, there are numerous challenges that are presented by future missions, which includes improving the petabytes of data quickly, provide seamless data and information discovery, while also keeping all this into an open data policy. So the data is free and openly available for anybody to use for any purpose. So obviously, we're looking at emerging technologies to address these challenges. First, the program has adopted a vision to develop and operate components of data systems in the commercial cloud environment that will meet the needs of future missions with high data rates and provide improved data management and user access to many ongoing Earth science missions. This transition to commercial cloud also presents new opportunities for users to process data in place in cloud and perform analytics at scale. We are doing all of this, again, making the data freely available to anybody to use. The second technology is more data-driven, where we are focusing on 3 things. Number 1 is the maximizing the information and knowledge discovery capabilities from our archives. Number 2 is augmenting data stewardship processes, and I'll get that in detail a little bit later. And number 3 is addressing the science research and application needs, right? Having such a vast amount of data, can we do science on a data-driven approach rather than hypothesis-driven approach? The main focus of the talk is on the data-driven technologies, focusing on these 3 areas today. But drilling down a little bit on the cloud computing, it is not only the archival needs that we are addressing, we also want to prepare data users to maximize the amount of data expected from these large missions. The commercial cloud provides an elegant alternative to downloading huge amounts of data from the archive, right? We want users to come to the and use the data and analysis close to the data. Drilling down on the data-driven technologies, the main focus is around the artificial intelligence and machine learning. I'm sure most of you are already familiar with the term AI and ML, but the figure here is, in a nutshell, summarizes what these terms mean. Artificial intelligence is defined as the science and engineering of making intelligent machines, which is a field within a computer science area. Machine learning is a subfield of artificial intelligence that uses statistics and mathematical models to find patterns within the data. Finally, the deep learning is a subfield of machine learning that uses algorithms with layers of artificial neural networks to learn from the data and make decisions. While there are a number of techniques used within AI communities, machine learning is rapidly being adopted across academia and science and industry. Deep learning that attempts to learn from the data in a manner similar to that of a human brain is a technique that is being used with rather increased frequency nowadays. Deep learning techniques are classified as either supervised or unsupervised. Supervised learning rely on a known set of questions, and it gives you an output, which are answers to learn a prediction or a classification, while unsupervised learning learn independently with minimum human interaction. To date, I think most of the practical applications of AI are in the supervised learning side of the things. The acceleration and rapid adoption of these AI ML techniques within the industry is fueled by these five things that I'm showing here, and that these five things have definitely helped adoption of AI ML within the NASA Earth Science as well. So let's look at the three things, three needs that we are trying to address using AI and ML. The first one is to maximize information and knowledge discovery capabilities, which is what I would demonstrate with the phenomena portal concept. So why are we developing this phenomena portal for our data systems? The reason behind this concept is that even though Earth science data archives have significantly increased in size due to the reasons I mentioned earlier, advanced sensors and just number of high-rate missions that we're going to get in the future, the Earth science data systems have not taken advantage of these data-driven technologies yet to provide advanced search capabilities. What I mean by that is that the search capabilities are limited to predefined sets of facets. Therefore, users need to know ahead of time what those facets are, what geophysical parameters are relevant to what they want to study, and so on. Imagine searching for 34 petabytes of data with such a search query today and about 250 petabytes of data in 5 years' time. That's not efficient at all, right? Therefore, there's a need to develop innovative data management to allow exploration of large Earth science archives with non-traditional approaches or novel approaches. What we have realized is that most early career Earth science or geoscience researchers and users or grad students start their study or their research based on a use case of Earth science events. With that in mind, this work provides automated event detections, which is used to catalog Earth science events in an event database, allowing a novel way to explore large archives of data. So here is an example of typical data exploration that we currently support. Let's say a grad student wants to study fire events. Fire is particularly important because fire smoke emits a large amount of harmful pollutants into the atmosphere. These plumes also impact air quality, visibility, and so on. So in the case of fire, users could go to a visualization tool such as NASA Worldview, where the user notices the smoke in an imagery like this that I've shown. Then to further investigate, the user can turn on a thermal layer that is already existing, right? And you can see the red dot there indicating there's a fire. And the next step is to use a search tool to find the science data relevant to fire using a search interface like this. In this case, user can type in a search term called fire, use the data and date and time that you're interested in. And you get a list of data files, you download, you do your analysis, right? Alternatively, what if you could let the machine learning algorithms to identify all the data with fire events? This video demonstrates the performance of a machine learning model for smoke detection that was applied to the Kincaid fire in October of 2019 in California, the same fire that we saw earlier. The color indicates the probability of the pixels being a smoke pixel or not. We trained a custom pixel-based convolutional neural network to assign probability whether a pixel is a smoke or not pixel. Here, the data is available every 15 minutes, so we can do this detection every 15 minutes if we scale it up. The trained model is applied to satellite imagery, and we can determine whether the smoke is, where the smoke is and how it's evolving. So the previous example was a bit easier, right? Because the NASA worldview visualization tool already had a thermal layer that could be used for hotspot detection for fires, and then we would know exactly where to look for. What if the event was something else, such as this high latitude dust? High latitude dust plays an important role in modulating atmospheric and oceanic processes important for climate applications. Currently, there is not a good way of cataloging these high latitude dust events because the current way of identifying these are using the ground sensors, which are few and far in between. So can we automatically capture the occurrences of these high latitude dust in regions that are susceptible to these phenomena? So here you see a result of applying a deep learning technique, specifically a custom neural network again, convolution neural network to be specific. The color again indicates the probability of pixels being a dust pixel or not a dust pixel. Here is another type of event, something called transverse cirrus bands. Transverse cirrus bands are ice clouds that often form in association with other weather phenomena such as mesoscale convective systems, hurricanes, and jet streaks. And these transverse cirrus bands are often associated with a clear air turbulence, so it has implications for air traffic. Here we adapted a VTG network and something called transfer learning, then localize the events. We could localize where in the image are these transverse cirrus bands. So these are the three phenomena that we looked into. Once the model is evaluated and optimized, the model is deployed in a production. Once deployed, the system automatically triggers a pipeline for new models to be executed. Any new predictions is performed with the new model. Any detected events is saved in a database, which is served through an API, creating through an API so that the applications like this portal can use it. So let me just do a quick demo here. So once you first go into the portal, you get an overview page of how many events, how many types of events, how many were detected. And this provides a way for early career scientists or people who want to study events to go there and quickly look at these occurrence of these events over time. And one can even do a climatological study based on this. And it also has a way to provide feedbacks along with informative pages like what the event is about, how we're doing the detections, and things like that. As the demo is moving, I will explain what's going on here. So if you go to a map view of the product, you see these grids where it's sort of a heat map, which allows you to see where the hotspots are for particular events. You can turn on and off each event, and also change the confidence level in terms of if you want to see only high probability of these events. And if you want to do your own study, then you look at the actual information and download the data yourself and do your analysis locally. So that was an example of providing a data-driven search system to complement existing search system within the data system. And ultimately, if you zoom enough, you can see the images that were being used to make the predictions. For example, this is a smoke case where exactly you see the images that were used with high confidence to locate those the event. So next issue we're trying to address is the augmentation of data stewardship processes, especially automating some of the subjective tasks to provide a consistent method. We again leverage AI and ML for such automation. One project that we have addressed is related to the keyword assignment to metadata records. So NASA's growing collection of Earth science datasets are described by metadata records stored in a catalog called CMR, Common Metadata Repository. It leverages controlled vocabulary of science keywords, which is a hierarchical set of controlled information. And these science keywords are used to help ensure Earth science data are described in a consistent and comprehensive manner. These science keywords are manually assigned to datasets by data curators using the best of their knowledge about the data. Assigning keywords manually is labor-intensive and is prone to human error and, in most cases, subjectivity and inconsistency. Therefore, the error and inconsistency can propagate into search and discovery of these datasets. So we want to address those issues. So our solution to this problem was leveraging machine learning to accurately assign science keywords to these datasets in an automated and objective and also consistent manner. So what we did was we developed a keyword classifier that takes word embeddings, and I'll describe what that is in a little bit, for metadata abstracts as an input. The results of the classifier are suggested keywords along with their probability scores. So this is more of a natural language processing side of the thing. So I can see some similarities with what you guys do, since this is more textual based application. So I want to give you a short background on a key concept used here called word-to-vec. Word-to-vec is a neural network used to construct vector representation of words called word embeddings from text. Word embeddings break down words into latent variables, each of them capturing hidden relationships present in the corpus. Word embeddings are universal feature extractors and can be used for various classification tasks. In our case, we trained an Earth science-specific word-to-vec. Word-to-vec embeddings was built from a science corpus that captures the domain-specific relationship between words in the corpus. So our implementation was trained on a corpus that was about 88,000 Earth science journal papers, with the intent that such a large corpus would capture domain information in a lot of detail. So we use that word-to-vec to obtain a word embeddings for our abstracts. The embeddings are used as an input to the neural network, which was trained to assign relevant keywords based on an abstract. We also built a web service for users to enter abstracts and retrieve corresponding keywords. So essentially, word-to-vec is a neural network. The result of the word-to-vec layer is fed into another neural network for classification purposes. So here you can see an interface that we built on top of the web service. The tool takes a metadata concept for data sets and suggests keywords, and it also allows users to correct existing keywords that already exist in the database. So right now you see the concept being added, and you'll see a abstract and the suggested keywords, and users can pick whether it's correct or they want to fix it. Moving on to another application of data-driven methods in detail. This application will be the one I'll be talking in a little bit more detail. This is an example of using the artificial intelligence on vast amount of science data that we collect to address a specific and very important science problem. The problem relates to estimating tropical cyclone intensity. By tropical cyclone, I mean hurricane, which is the wind speed of the storm using satellite images. During a tropical cyclone, the main factors that contribute to the resulting devastation, damage, amount, are often attributed to the cyclone's wind speed. Therefore, being able to accurately estimate tropical cyclone's intensity, or in this case, wind speed, is very critical for disaster preparedness and response. But before we get to the application, I wanted to share with you this study that my group did looking at papers in these 4 major journals where earth science researchers publish their result. We looked at what's the trend been for the last 10, 11 years in terms of machine learning and AI in earth science. And you see it has increased by quite a bit. So this gives you some perspective on where the science is going in terms of AI and ML, right? Typically, these papers that we looked at and most other papers address a problem in the domain and follow this workflow or a life cycle where they acquire data, clean the data, and make it ready for algorithms, machine learning algorithms in this case, then develop a model, train the model, and refine it. And it's an iterative process. You go back if you see some issues and fix the data and all that stuff, right? Until it produces a reasonable accuracy. And they usually publish a paper if the accuracy is better than what's in the what's the state of the art, right? And most cases, the research stops there. However, there are additional steps in machine learning lifecycle that majority of research or application papers do not address, and those are deployment of this model in a production environment and utilizing the model output in an intuitive way so it can be used in practice. The application that we have implemented follows this end-to-end machine learning lifecycle. So why did we develop this system? To explain that, let me first show you an advisory from National Hurricane Center for a major hurricane in 2017. It was for Hurricane Ophelia. Here's the advisory. So what stands out in this advisory? Anyone? I guess everybody's muted, so I won't hear it. But now, can you see what the issue is here? So 2 human experts at 2 different forecasting centers, their estimates differed by 20 knots. 20 knots is, 1 knot is about 1.15 miles per hour in their analysis. And another one was actually 12 knots lower than either of them. So the issue with this approach is that it is very subjective to experts, right? And the reason it's subjective is the current approach is based on 70s technique developed by Dvorak that uses a human pattern analysis on satellite images. Typically, the outer curvature of the cloud and the coverage, the outer curvature of the cloud and the coverage are used to match a template like is shown here to determine the wind speed intensity. So that introduces human subjectivity. Therefore, you saw the different estimations from different forecasting centers. Furthermore, the human inspection is very time consuming, right? And estimation cannot be done at the pace of data being collected nowadays. So we wanted to apply machine learning technique to objectively determine such a pattern, to determine intensity automatically, and to do it as frequently as new data is being captured. So when we follow our machine learning lifecycle, the first thing we did was we collected the data. To create a consistent training data set, we had to develop a downloader for various catalogs and put them in a consistent form. For most cases, data required to train the models are labeled using image labeler, as shown here. This is a tool that we built in-house. The image labeler tool directly interfaces with satellite images, image databases, and allows labeling of images in a distributed environment. Additionally, the image labeler tool generates a machine learning ready data structure, so we don't have to massage it after we retrieve the data from the image labeler. For the case of hurricane intensity estimation, we compiled about 2 decades worth of hurricane images that result in about 100,000 images. Additionally, we use the Storm database that also provides us with intensity information and such. So we use the data from year 2000 to 2017 for training our model, 2018 for validation of our model, and 2019 we actually let it run in production and saw its evaluation. In terms of model development, using the training data set that we collected, we designed a deep learning model for the objective estimation of tropical cyclone intensity using a custom convolution neural network on satellite images. Development of this model required several iterations through the machine learning lifecycle to arrive at a final model configuration, like is shown here, where the final layer is a regression model rather than a classification model. The chart here demonstrates the training and validation accuracy. The loss is shown as a mean squared error here. We also compared with to create a detailed look at a particular hurricane in 2010 called Hurricane Earl. As you can see, the correlation with the observed wind speed is fairly accurate here. So we reached about 7.8 knots, which is better than root mean square error, which is better than what you could find in the state of the art. So our first thing was, let's publish a paper. So we published a paper and our research was complete, right? But we want to go a little bit further. So what do we do now? The question is, can we put this model in production environment? However, there are two main reasons for most models that do not end up in production. The first one is a trust factor. What do I mean by that? One of the major criticisms of machine learning techniques from the domain experts or the subject matter experts is that it is very difficult to determine what the model is actually learning to make these decisions. Therefore, there is a trust factor between machine learning experts and the physical science community that hinders this transition from research to production. The second reason is that transitioning models from research to production is just too complex. So to address the first issue, we started investigating whether we could interrogate the model and demonstrate what the AI is relying to make the decisions. We looked at a technique to see a response from each neuron at each layer as presented by these researchers. And we applied that to our hurricane model. And here's the feature output, at least the prominent one that you can see for each layer. In this case was, can't read that, I believe from the feature map from layer 3. Here's another technique related to the first one that we found could be used for model inspection. This is more of an interactive tool to build intuition using visualizations. This interactive visualization shows every neuron in a trained convolution neural network as it responds to an image. So it looks a little chaotic, but when you apply it to the hurricane model here's a case of all 8 categories of hurricane, and this is the output you get. However, the technique that the domain experts felt most intuitive is this technique called the class activation maps. A class activation map for a particular category or a class indicates the discriminative image reasons that was used by the model to identify its category. And it's done by using something called a global average pooling method instead of doing a final output layer. So it produces this heat map that can be used to identify which feature, not only which features, but the location of those features within an image. So when we apply that to our model, this is the result we get. Encouragingly, the features and the location of those features that contribute most to the model output are also present in the cloud patterns used within the Dvorak technique that I mentioned earlier. As you can see, as I advance here, this is for category 1. Category 2, you can see the features are getting keying in on around that eye of the hurricane, and so on. So here's a demonstration of the class activation maps for Hurricane Dorian. Hurricane Dorian, as if you remember, it devastated Bahamas, making landfall and stalling as a Category 5 hurricane for a long time. To the left here, you see the infrared imagery from GOES satellite, which is an input to the model. In the middle is the class activation map that provides detailed information about the most prominent features in that image that contribute to the classification as shown on the image. To the right is the corresponding Dvorak enhanced brightness temperature variable, and that's usually being used by some algorithms to determine the intensity. At the bottom left, you see the ML estimate in green and the actual forecast advisory from National Hurricane in black. And to the bottom right, you see the geographic location of the eye of the storm. So this animation, which I'm going to start now, shows the life cycle of the Hurricane Dorian from August 24th to September 8th of 2019. So a comparison between the CAMs, the class activation maps, and the Dvorak enhanced brightness temperature on the right shows that as the storm intensifies, the important features of classification transitions from the outer bands of the hurricane, where it's not so organized, to the central dense overcast region, right? As soon as it hits Category 3 or 4, it's mostly keying on the central part of the hurricane. I'll let the animation run for a little bit. And if you look at the bottom, when it was the intensity was low, there was little disparity between the forecast versus the ML prediction. But as it grew, the intensity is intensified, it was actually fairly accurate. All right, so far we have the model, and there is a trust from the domain experts, and we have somewhat explained the black box of AI model. Now, can we go that extra mile and put this model into production? Like I mentioned earlier, putting the model in production is a difficult task. Before we do that, we need to ask a few questions. How do we measure the confidence of the model over time? Meaning that the incoming data will change, right? Data is going to be different. As we apply the model over time, do we need to train more? Which means that we'll have a new model, right? How do you address those things? So it's not that easy. More considerations need to be given to things like, will the data format change of the input data? What are the requirements? Maybe the latency will change, right? In some cases of disasters, people want information as quickly as possible. We know that we need to update a model eventually, but how frequently we do that and how frequently we retrain it. These are questions that not only spans machine learning, but also software engineering side of things, right? If we do now testing, right, can we get an indication of whether our model is faltering? Can we get an early warning for that? And so finally, after considering all production-related questions, we built a situational awareness portal for hurricane wind speed estimation. The idea is that whenever there is an outlook posted for storms, the system starts to collect images and starts predicting the wind speed in much higher temporal frequency. Users can visually see the storms in the map with many additional contextual information as layers and also compare the National Hurricane Center observations with predictions. And this is the workflow for our event-based estimation system. For imagery input, as the satellite captures the data, it is transferred into ground station, then it gets processed into images, which then goes into a database that we access. The requirements for the system were collected using a set of surveys, as you can see one example here. For the user interface design, we focused on clarity, having a very intuitive interface. We focused on interactions. We wanted people to interact with the system. And we wanted to have users be in control of that. We also realized that strong visual hierarchies work the best. So we provided an overview first and then allowed users to drill down further using filtering mechanisms. We also looked into existing hurricane portal, not for the same case, but similar types of hurricane portal, informative portals, and tried to include the features that the domain experts considered useful. For example, here's an example from NOAA, how they've implemented a hurricane portal, informative portal. And this was from Google, I believe, where they have an information card explaining the more information about the hurricane itself. So we tried to incorporate those in our system development. So due to the event-based production system requirement and an iterative aspect of model transition, a cloud computing native solution was chosen, and specifically the Amazon Web Services which used here. Training of the model was done on-premise GPU servers because it was too expensive to do it in the cloud at that time. After the model is trained, the model is uploaded to AWS S3 bucket for use within the production system. And after it was dropped, the future inferencing automatically used the newest model in the bucket. The service stack was deployed in using the AWS CloudFormation deployment, and we also implemented some CloudWatch rules to figure out when to use the new estimation process. The machine learning model executes on a AWS ACS cluster, and results are stored in the Amazon RDS database. And they are then served to the portal or for anybody to consume using API gateways. The portal the system's UI is statically generated site, and that invokes separate APIs to retrieve the data from the image database. The front end is developed using the React and Redux framework to provide the view and state management frameworks. The display includes the Mapbox GL front end. And the whole reason for using the AWS is to provide this stable production environment and a scalable solution when there is a demand, like the hurricane season. Before I get to the demonstration, I wanted to mention that this was a well-coordinated effort with machine learning researchers, making the data ML ready and then developing the model. They worked in close collaboration with the domain experts in terms of evaluation, creating performance baselines, and also addressing the issue of explainability. The end users, stakeholders provided the production requirements for the system, and ML engineers were able to take the AI artifacts and deploy into the production environment. They were able to transform the ML outputs prediction into a meaningful visualization and add other contextual information along with the scaling of the system in the AWS environment. Finally, putting it together, here is our complete machine learning lifecycle for the hurricane intensity estimation portal. When you first go there, you see an overview of all the hurricanes, and you can select one particular hurricane and drill down. And you can get the prediction information by selecting those information card and look at the actual image that was being used for determining the wind speed. You can also go and look at historical hurricanes, look at how those were being estimated in terms of machine learning perspective, and compare that with the National Hurricane Estimate. You can also add additional layers. For example, in this case, you can select the sea surface temperature. What was the sea surface temperature like when this hurricane occurred at certain locations? And things like that. Additional information provides context to the genesis and progression of these events. So there is a hurricane right now. There are multiple hurricanes, I believe. So I encourage you to go and look at it. It's the URL is hurricane.dsig.net, hurricane.dsig.net. Some of the challenges and lessons learned during this implementation are shown here. From the ML model development perspective, this being a supervised learning algorithm, we needed a large-scale training data set. Even though we were able to collect the data from different sources, we had to spend a considerable amount of time cleaning and removing inconsistency in data. Explaining why the model works to the domain expert was particularly difficult. From the software engineering and software development perspective, it was difficult to version the training data, model, algorithms, and source code together, which resulted in DevOps and CI/CD taking a whole different meaning. And finally, there were complexity with evolving platforms, frameworks, and libraries and infrastructure. They change very frequently, right? So keeping up with all those is a difficult problem. So you might ask, what's next for us? We are trying to address the problem of training data sets to scale some of these, accelerate some of these machine learning algorithms from the data systems perspective. When you look at the advancements in machine learning, source of all progress can be tracked back to data, right? But I believe the progress is starting to plateau in terms of these machine learning advancements. The low-hanging fruits have mostly been plucked. As the models get complex, feature maps, like I showed earlier, and the transformations functions that we use in some of these algorithms have lots of data-dependent parameters. Good generalization requires a lot of data. In some cases, millions of data points, and that requires tens of thousands of training data sets. So we're trying to address that from the data systems perspective. Finally, as I showed the data lifecycle earlier, we are trying to strategically infuse artificial intelligence and machine learning into the data lifecycle that I mentioned earlier. And you can see some of the examples of those initiatives. Thank you. That was my last slide. I hope it was informative. And if we have time, I can take some questions.